In the world of automotive engineering, trucks are often seen as the ultimate symbol of strength and reliability. They're expected to haul heavy loads, survive harsh terrain, and endure years of wear and tear without faltering. Yet, behind this image of invincibility, there are instances that challenge our perception of what a pickup truck can handle. Some models, despite their rugged exterior and powerful engines, have displayed shocking structural weaknesses that have left owners and experts alike questioning their safety. This video delves into one of the most extreme automotive failures: pickup trucks that have actually cracked in half while driving. While this sounds like an exaggeration, it is a real phenomenon, and understanding the circumstances, causes, and consequences behind these incidents is both fascinating and alarming. From design flaws to manufacturing oversights, the stories in this list reveal that not every truck lives up to its promise of unbreakable strength. Number 12. Early 2000s Ford F-Series. The early 2000s Ford F-Series trucks were highly popular, but some models revealed notable frame vulnerabilities. Under conditions of heavy towing combined with uneven terrain, certain frames developed cracks that could spread quickly, raising safety concerns. The problem stemmed from a mix of material fatigue and inconsistent manufacturing processes. Some frames had welds that were misaligned or incomplete, which compromised the steel's strength and caused fractures over time. Although such failures were not widespread, the potential consequences were serious enough to trigger recalls and subsequent design improvements. The F-Series performance in everyday conditions remained strong, but extreme usage highlighted the importance of robust frame engineering. Engineers later addressed these issues by refining weld techniques, using higher quality steel, and reinforcing critical stress points. The scenario emphasizes that even high-selling vehicles can reveal structural weaknesses when subjected to sustained heavy loads. Regular inspections became an essential practice for owners, ensuring early detection of stress or cracks before they could worsen. This situation demonstrates how real-world conditions often uncover limitations that testing environments may not fully capture. Over time, Ford adjusted its manufacturing protocols and material specifications, resulting in later F-Series models with significantly enhanced durability. For truck owners, this example highlights the interplay between design, maintenance, and real-world performance, showing that vigilance matters even for top-selling vehicles. Number 11. Late 1990s Chevrolet Silverado 1500. The late 1990s Chevrolet Silverado 1500 is known for durability, yet certain models faced unexpected structural challenges. In colder regions where road salt was heavily used, frame rust appeared earlier than anticipated. Rust developed at critical load-bearing points, gradually weakening the structure and increasing the risk of splits under heavy stress. While not all vehicles experienced this problem, affected trucks demonstrated how environmental factors can accelerate material degradation. Chevrolet responded by reinforcing frame components in subsequent models and providing guidance for owners to conduct regular rust inspections. Preventive maintenance became a crucial strategy for preserving the truck's structural integrity, illustrating the importance of proactive measures alongside strong engineering. The Silverado's overall design was solid, but real-world usage, especially in harsh climates, revealed vulnerabilities that routine testing might not detect. By addressing these weak points, Chevrolet improved durability and extended the operational lifespan of future vehicles. Truck owners who monitored for corrosion and acted promptly avoided more severe structural problems. These adjustments highlight the role of iterative design improvements and informed maintenance practices in vehicle longevity. In this scenario, environmental exposure and usage patterns were just as significant as material and design choices, emphasizing that even vehicles with excellent reputations require attention to prevent deterioration under challenging conditions. Number 10. Mid-2000s Dodge Ram 2500. The mid-2000s Dodge Ram 2500 encountered a small number of frame issues, primarily under heavy towing or construction use. Some trucks reported mid-frame cracks, often linked to stress concentration points around the cab and bed mounts. These fractures resulted from metal fatigue, which standard tests may not fully simulate. While Dodge's engineering was generally reliable, real-world usage exposed vulnerabilities that became apparent only under extreme conditions. The incidents prompted discussions about designing frames capable of handling heavy workloads without significant weight increases. Investigations revealed that trucks subjected to maximum payloads or uneven terrain were most at risk, highlighting the connection between usage intensity and structural performance. Dodge subsequently analyzed stress points and considered design enhancements to mitigate fatigue in critical areas. Owners learned the value of monitoring for early signs of wear and reinforcing load management practices to reduce the risk of frame damage. This example underscores the dynamic relationship between design, material selection, and practical application. Even robust engineering solutions must account for the realities of extreme or continuous use, where stress accumulates in unexpected ways. The mid-2000s Ram scenario demonstrates that thorough inspections, load awareness, and careful engineering refinements can prevent small weaknesses from becoming significant structural failures, ultimately extending the service life of heavy-duty vehicles. Number 9. Early 2000s Nissan Titan. Early Nissan Titan models experienced isolated frame failures when subjected to off-road conditions or heavy towing. Investigations showed that mid-frame fractures often resulted from a combination of material choice and welding techniques, with stress accumulating at critical areas. Vehicles carrying overloaded cargo or navigating uneven terrain were particularly prone to these problems. Nissan addressed the issue by increasing frame thickness in high-stress regions and reinforcing welds in later iterations. These improvements ensured that the Titan could better withstand demanding conditions without compromising overall performance. The situation demonstrates how small design adjustments can significantly enhance durability while maintaining operational efficiency. For owners, understanding weight limits and inspecting structural components became essential practices to prevent damage. The Titan scenario highlights the importance of aligning real-world usage with engineering specifications, as extreme loads or terrain can reveal vulnerabilities not immediately apparent during standard testing. By addressing these weaknesses, Nissan improved reliability and reduced the likelihood of mid-frame fractures in subsequent models. The experience illustrates how iterative design and attention to stress distribution play a critical role in vehicle longevity. Over time, these refinements enhanced performance consistency, making the Titan a more resilient choice for drivers who rely on heavy-duty trucks for both work and recreational use. while emphasizing the ongoing interaction between engineering, materials, and practical application. Number 8. Toyota Tundra, late 2000s. The late 2000s Toyota Tundra, though highly reliable, had reports of mid-frame cracks under heavy-duty hauling conditions, especially in mountainous or uneven terrain. The fractures were primarily caused by a combination of metal fatigue and torsional stress, which gradually exceeded the frame's structural limits. Trucks subjected to repeated high loads exhibited more pronounced stress accumulation, particularly near critical mounting points. Toyota responded promptly with comprehensive safety audits to identify potential weaknesses and implemented chassis reinforcements in subsequent model years. Engineers focused on strengthening high-stress areas without compromising overall truck performance or weight distribution. This proactive approach highlights the value of iterative design, where minor early weaknesses inform future improvements. Owners of affected trucks were advised to monitor for unusual flexing or stress marks, ensuring preventive measures could be taken before cracks developed further. The situation also emphasizes how even well-engineered vehicles can encounter rare structural challenges when exposed to extreme usage patterns. Toyota's response demonstrates the importance of balancing durability with real-world operational demands, showing that small adjustments in design and reinforcement can significantly extend service life. The Tundra example illustrates that vigilance in monitoring stress points, combined with manufacturer improvements, ensures both safety and long-term performance, reinforcing the principle that preventive maintenance and thoughtful engineering go hand in hand. Number 7. GMC Sierra 2500 Early 2000. The early 2000s GMC Sierra 250 faced frame durability challenges similar to related models in its class, particularly when hauling maximum payloads. Mid-frame cracks were reported in trucks frequently exposed to heavy-duty workloads, often developing over time due to cumulative metal fatigue and stress at key structural points. Environmental factors, such as moisture and road salt, accelerated corrosion in some instances, further compromising the frame's integrity. GMC responded by reinforcing frames in later models, focusing on high-stress areas near mounting points to enhance durability. Owners were advised to inspect older trucks regularly for early signs of cracking or corrosion, emphasizing preventive care as an essential aspect of maintaining performance. The incidents underline how even robust designs can reveal vulnerabilities under extreme usage, particularly when trucks operate near their maximum capabilities. Maintenance routines, including monitoring stress points and corrosion-prone areas, were key in mitigating potential failures. GMC's updates included improved welding techniques and stronger steel reinforcement, demonstrating the value of addressing structural weaknesses proactively. The Sierra 2500 scenario highlights the balance between engineering design, real-world workload, and maintenance practices. By combining careful inspection with manufacturer improvements, owners could preserve the structural integrity of their trucks, ensuring continued safe operation under heavy-duty conditions. This example reinforces the importance of monitoring and intervention in extending the service life of large, demanding vehicles. Number 6. Ford Super Duty F350 Mid-2000s. The mid-2000s Ford Super Duty F350, known for its towing capacity, experienced isolated frame issues under extreme conditions. Reports indicated that heavy towing combined with uneven road surfaces sometimes led to cracks near the cab or midsection. While rare, these failures highlighted the limits of steel when repeatedly subjected to high torsional and bending stresses. Ford's engineering team responded by redesigning critical frame components and adding additional welding reinforcements in later models to improve overall resilience. Investigations identified stress concentration points as the primary locations where fractures were most likely to occur. Owners of early models were advised to monitor structural integrity regularly, particularly if frequently towing at or near maximum capacity. The scenario demonstrates how extreme workloads can reveal weaknesses not evident during standard testing procedures. Ford's proactive adjustments involved refining material strength and reinforcing high-stress zones, ensuring that later trucks could better withstand demanding conditions without significant weight increases. The F-350 example shows how continuous evaluation and adaptation of vehicle frames are essential to maintaining performance under heavy-duty usage. It also underscores the importance of balancing structural reinforcement with operational efficiency, ensuring trucks remain capable while avoiding unnecessary weight penalties. Observing proper load limits, routine inspection, and engineering improvements together contribute to extended longevity and safe operation of heavy-duty pickups under extreme working conditions. Number 5. Ram 1500 2010s. Certain 2010s, Ram 1500 trucks exhibited frame reinforcement weaknesses under extreme stress, resulting in partial splits in rare cases. The fractures often developed around suspension mounts and other stress concentration points, where repeated loads caused localized fatigue over time. Engineers identified these vulnerabilities and modified the frame in later production runs, reinforcing critical areas to improve overall structural integrity. Regular usage within normal limits did not generally trigger these issues, but heavy-duty applications or extreme off-road conditions revealed the truck's limitations. Owners were encouraged to inspect high-stress points and maintain proper load distribution to reduce the risk of frame damage. These improvements reflect a broader trend in truck design, where iterative reinforcement addresses specific vulnerabilities without compromising performance or ride quality. The Ram 1500 example illustrates the importance of monitoring structural stress in real-world scenarios, as laboratory testing cannot always replicate repeated extreme loading. Updates included enhanced welding techniques and localized frame strengthening, ensuring later models could handle rigorous use more reliably. The experience reinforces that even modern trucks require attention to stress-prone components, emphasizing the interplay between design, materials, and operational conditions. By addressing potential weak points proactively, manufacturers can enhance durability while preserving the truck's intended functionality, demonstrating the ongoing evolution of heavy-duty pickups to meet the demands of their owners and the environments in which they operate. Number 4. Ford Ranger, late 1990s. The late 1990s Ford Ranger, designed primarily for lighter-duty work, experienced occasional frame cracks when subjected to loads beyond its intended capacity. Overloading and off-road usage were the main contributors, with stress accumulating at key structural points over time. Investigations revealed that repeated torsional stress could cause small fractures that, if left unaddressed, could worsen and compromise the truck's integrity. While these incidents were uncommon, They highlighted the importance of adhering to load limits and monitoring the frame for early signs of damage. Ford reinforced certain components in subsequent models to enhance resistance to bending and torsional stress, demonstrating a proactive approach to addressing structural weaknesses. Owners of affected trucks were advised to conduct regular inspections, particularly focusing on mounting areas and undercarriage sections most susceptible to stress. These practices help identify minor issues before they escalate into significant failures, ensuring safe operation. The Ranger example underscores that even smaller trucks are not immune to structural fatigue under extreme conditions. Engineering adjustments, combined with careful use and maintenance, contribute to longevity and reliability. By analyzing patterns of stress and reinforcing weak points, manufacturers can extend the functional lifespan of light-duty trucks. This scenario illustrates the balance between design limitations and operational awareness, emphasizing that vigilance and preventive care are critical for maintaining truck performance. Number 3. Chevrolet Colorado. Early 2000s. Early 2000s, Chevrolet Colorado trucks, built for moderate workloads, occasionally developed mid-frame cracks under heavy use. Vehicles frequently carrying substantial payloads over uneven terrain were most susceptible, as repeated stress caused fatigue in areas with insufficient reinforcement. Investigations found that material properties and structural design in certain high-stress zones contributed to these fractures, which often occurred gradually. Chevrolet addressed these vulnerabilities in later models by strengthening critical sections of the frame and improving welding processes, enhancing overall durability. Owners of affected trucks were encouraged to monitor for early signs of stress, such as unusual flexing or minor cracks, as timely detection helped prevent more serious damage. This proactive approach illustrates the importance of both design adjustments and routine inspections in preserving structural integrity. The Colorado's experience demonstrates how moderate-duty vehicles can encounter stress-related issues when operating beyond their intended limits. By refining reinforcement techniques and educating owners on preventive care, Chevrolet improved both safety and longevity in subsequent production runs. The situation highlights the interplay between material strength, usage intensity, and maintenance practices. Regular monitoring of high-stress areas, combined with manufacturer improvements, ensures that trucks continue to perform reliably under moderate workloads. The Colorado example reinforces the lesson that even vehicles designed for lighter use require attention to structural stress, emphasizing the ongoing importance of maintenance and thoughtful engineering. Number 2. Toyota Tacoma, late 1990s. The late 1990s, Toyota Tacoma, widely regarded for reliability, had isolated reports of frame cracking in trucks, frequently exposed to heavy off-road use or substantial cargo loads. Despite its compact size, the vehicle was susceptible to torsional stress, particularly in the midframe and suspension mounting points, where repeated loads accumulated over time. Investigations indicated that material fatigue combined with insufficient reinforcement in certain areas contributed to these fractures. Toyota addressed the problem by enhancing frame strength and revising welding practices in later models, focusing on zones most affected by torsional forces. Owners were advised to monitor the undercarriage and mounting points regularly, ensuring early detection of minor cracks before they developed further. The Tacoma scenario highlights that even smaller pickups experience structural stress when exposed to heavy-duty conditions, emphasizing the need for responsible usage and preventive maintenance. Engineering adjustments improved durability without compromising the truck's overall performance or agility, demonstrating the importance of targeted reinforcement in design evolution. By combining careful inspection routines with manufacturer updates, the Tacoma maintained its reputation for reliability while mitigating rare but serious structural concerns. This example underscores the balance between vehicle design, operational limits, and ongoing maintenance, showing that attentive care and engineering improvements together ensure long-term durability for compact trucks under demanding conditions. Number 1. Nissan Frontier 2000s. The 2000s, Nissan Frontier encountered rare frame issues under extreme operational conditions. Trucks frequently overloaded or repeatedly exposed to uneven terrain, experienced stress accumulation in critical frame areas, occasionally resulting in fractures. Investigations highlighted that material choice and welding techniques contributed to these vulnerabilities, with cracks most commonly appearing near suspension and mounting points. Nissan responded by reinforcing key frame components and improving welding processes in later models to enhance durability. Owners of earlier trucks were advised to monitor high-stress areas for signs of fatigue, ensuring minor issues could be addressed before escalating into significant structural problems. The Frontier scenario demonstrates how even well-designed mid-size trucks can encounter localized stress failures when exposed to rigorous real-world usage. Engineering refinements focused on distributing loads more evenly across the frame and strengthening areas prone to repeated bending. Regular inspection, combined with these design improvements, became a key factor in maintaining safe operation and prolonging service life. The experience emphasizes the ongoing evolution of truck design, where iterative improvements address previously unforeseen weaknesses. By identifying stress-prone zones and enhancing structural reinforcement, Nissan increased both reliability and resilience. The Frontier example reinforces that preventive care, coupled with thoughtful engineering, is essential for preserving truck performance under demanding conditions, ensuring that even small adjustments can significantly reduce the likelihood of structural failures and extend operational longevity. Trucks cracking in half might seem like an exaggerated headline, but, as we've seen, it has happened, and the causes are both fascinating and sobering. From material fatigue and design flaws to environmental stresses and overuse, these incidents remind us that even vehicles designed for the toughest jobs have limits. Studying these failures not only informs prospective truck buyers, but also highlights the importance of engineering, maintenance, and responsible usage. If you found this exploration of structural failures eye-opening, make sure to engage with the content, like the video, to support more in-depth automotive insights. Comment your thoughts on which truck surprised you the most, and subscribe to stay updated on fascinating automotive stories. The road to knowledge is paved with curiosity, and your engagement keeps it rolling.